Okay, Math 2400, Lecture 1, Probability. We start with the Section 1, in fact, and I follow the textbook as mentioned in the syllabus. So, sample space and events. A sample space is a collection of all possible outcomes of an experiment. We denote it by S, capital S. Event is any subset of the sample space S. Well, we can call an event which has only one outcome as a simple event, and more than one outcome we call it compound event. So let me give you examples here of events and sample spaces. So let's example. So suppose there are two gas stations on certain, say, street. So we have station A and station B. This has 4 pumps and also 4. Okay, and at certain time, say you can start at like 8 a.m. and you observe the number of people who are at each gas station, or let's say number of cars that are using pumps. So number of cars at each gas station goes from 0 to 4. So we have something like this, something like this is A and this is B, A 0, 1, 2, 3 and 4. 0 means no pump is in use, 2, 3 and 4. So we might have nothing, we might have this way is 0 and this way is 1, so this is like the first coordinate, this is the second coordinate, and we might have 0, 2, 0, 4. So this way it goes down to 4, 0, and up to here 4 times and 4. Okay, so we have these ordered pairs. Each one is called an ordered pair. It's like a x and y coordinate, and we can say that if we observe at some certain time, we just stop and count, we have a sample space like this, sample space of this experiment. So we are experimenting something, so the sample space is 0, 0, 0, 1, up to 0, 4, and it is 1, 0, up to 1, 4, and up to the last one, 4, 4. And we can write this is the way we write sets, so we can write it as A comma B, such that A and B go from 0 to 4. Okay, so we can either write all the outcomes, or we can write it in this abbreviated form. And well, this one has just 16, 4 times 4, 16 outcomes, so we can write down all of them, but most often it's too much. So we have too many outcomes, and it's preferred. This one is preferred. Well, anyway, so this is our sample space. Now, we can just pick a subset. Usually that subset is not just any subset. It comes with some, say, property. So for example, we can talk about event of, say, event E. We can talk about event E is when we have, say, an even number of cars at pumps in at each when we are doing that experiment. So this event is saying that A plus B is, and did I say even? Yeah, even number. Even number. Okay. So we can write it like this, and well, we should say that A and B go from 0 to 4. Or we can say, well, this is not 2 minutes, so we can come up with, say, considering 0 to be even, it can be 0, 0, it can be 0, 2, it can be 0, 4, and it can be 1, 3, and it can be 1, 1 can be, or 1, 3, and anything else here? No, nothing. Then we can have 2, 2, and nothing else, no, 2, 4 also. 2, 4, and oh, I forgot 1, 0. Did I? 1, 0, 2. No, 1, 0, 0. Sorry. What am I saying? 2, 0. Sorry. 1, 0 is not here. Well, 2, 0 is here. 2, 0, dot. So you can just write down all of them, or you can come up with a way to. This is the abbreviated way, and we prefer this one. But if we need the number of cars, I mean the number of terms in this one, or number of elements in E, then we have to come up with a way to count them. But anyway, this is like an sample space and the event of some experiment that really can happen in real life. So, but sometimes experiments are like, it just happens in your mind. So you can talk about something that is basically like some imaginary, so you don't have to do it, but well, you can do it. I don't know, it depends on the situation, but sometimes it is basically an example, like a mathematical example. Now, another one, which is a simple one, is say we roll 2 dice, for example. Okay, roll 2 dice. Now I'm not rolling 2 dice, but I can do that. So we can think of the sample space, and the sample space it depends on what we observe. So first is observe the 2 numbers. And the sample space here will be what? What are the numbers? The numbers are from 1 to 6, so it's very similar to the other one, except it goes from 1 to 6 and there's no 0. So it is A comma B, and A and B go from 1 to 6. Okay? So this is if we observe the 2 numbers separately, or we can observe the sum of the 2 numbers. Okay, so if we observe the 2 numbers separately, and the sum of the 2 numbers will be something like this. Now we can say if I have 1, 1, that's like a 2, and we can have 3, we can have 4, of 2, 6, and 6, that is 12. Okay, so that is the sample space. So depending on what we are observing, we can have different sample spaces from the same experiment. Now, this one, related to this one, we can talk about an event, E, to be, say, rolling 2 dice and getting an odd number. So an odd number will be A, B, the sum of them odd numbers, so A plus B is odd. Okay? We can also talk about this one and say rolling and observing the sum of the two numbers, then what's the event of observing an odd number. So these are, so in this one, this is an event. In this one, so let's number them S1 and S2. So this event is an event in S1. Okay, that's an event that happens in S1. Okay, so that is another one which I said you can just do it on a piece of paper, say. So we don't really have to roll two dice, but you can do that. You can do that. Okay, so these are now in both cases we can say do some mind experiment. Like for the dice, maybe we can say talk about something which I will explain. Like talk about the probability of getting a number, the sum of say 7, for example. Okay, so that was an event, and the sum set theory. We need a sum set theory here. Now, since I'm talking about sets and subsets, so it's good to know some set theory here. So we denote sets with like we can denote by anything. So it's a set, and so we have subset. So a set. This is called a Venn diagram. Venn diagram. You might have seen this in other classes. So a subset is like something inside the Venn S, so we say E is, so this is red subset or equal. So if you write E is a subset, not equal. We also say it is a proper subset, because a set is a subset of itself. Now subsets, two important subsets are the empty set, a subset of any set, and also S itself, S, the set itself. So these are the two extremes. A set, we assume that it is a subset of itself, and we also say that empty set is also a subset of any set. Not this one, this is just a subset of itself, or maybe a subset of something larger. Now, number 3 is the union of sets. Union of sets. So union is if I have two sets, say A and B. So we say A union B is in fact all x's, x's elements such that x is in A or in B. Okay, so union is like in logic, union is like OR. So OR is union. So what is in fact, what is it as a Venn diagram? Union, if these two are the sets, then union is basically this. So let me give you an example of a union. So if I have, say, A, B, C, D, say Z, and union with, say, A, C, say Z, K, F, or say something, then, okay, let's just put them together. A and A, you have to write it one time. B, the B is here. C, you write it one time. And D and Z, and A, C is here, there's a K here, and there's an F here, and there's an R here. Okay? So the ones that are common between the two sets are written one time. So in a set, every element is written just one time. Okay? So if you see that, well, in some, like in calculus, for example, when we discuss sequences, we sometimes write it like this and say A. No, that's not a set, that's something else. But if you give it an index, then you can say, you can put it in set format. And for it is intersection. So intersection, as you can guess, is this. So if this is A, this is B, then A intersect B, where's where? Let's write here. A intersect B, oh no, that's you. A intersect B, it goes the other way. A intersect B is all x's such that x in A and B. So you see intersection goes with and, so it should be in both of them. So, well, those two sets, what was that? From A, B, C, D, Z, I guess, intersect A, C, Z, F, R. Okay, intersection A is in both of them. A is here, A in A, then C is here, and Z is here, and nothing else. Is it correct? Yeah. A, C, and Z. So that is intersection. And one more thing is five, it is complement. Complement, well, some books use, so if I have set A, say, and I have universe, so this is, let's say it is S, sample space, and A is part of this. And complement is written in two ways, either we write it A, C, or in some books they write A prime. Either way, it is all x's in S, and such that x is not in A. So if this is A, its complement is what remains here, outside of A, inside S. Okay, so well, complement has to be with respect to a universe. So you cannot just say complement of set A. No, you have to say, okay, where does it come from? What set contains A, say? Okay, so then we can talk about complements. Now, I'm not sure what which one is this book using. I prefer this one to the A prime because they mix up this with, say, derivative, maybe. Who knows? Okay, so these were the, some notations here. Notation. Let me write down some notation. So notation that I use. There's this notation which belongs to. So we say that say A belongs to set A, B, C, D. Okay, and this, if I write this, does not belong. For example, this one I can say Z does not belong to this set. Okay. So belongs to, it's like a small epsilon. It's not epsilon, but it looks like epsilon. This is one I used No, I didn't use that. So we might we'll use it anyway. And another notation I used was I used the union notation. So this is union, and this is intersection. So if I use any other notations at some point, I will discuss it. I mean, or any concept. Okay. Okay, so we discuss the probability. So let's discuss the definition of probability. So that is two. In fact, what is probability and axioms of probability. Let me see what axioms are, with the way that it says. Okay, so axioms of probability, axiom number one is, first of all, what is probability? Probability is this. So let me, before saying anything, so probability is a set function. It is defined on subsets of S. i.e. events. But I should say some subsets, not every subset. Because not every subset of S is considered an event, right? So I would say, okay, certain subsets. Okay, I don't want to go too far into the theory, but anyway, when you talk about events, you might just ignore certain subsets and just talk about certain events, I mean, some subset of S, not every subset of S. Okay, so set function is this. So we have S here, and then we put the subsets of S here. So these are subsets of S. E1, E2, E3, so these are subsets, and the probability is in fact a function that is defined on subsets, and it takes these subsets that I have called events into the set 0, 1, so the interval 0, 1. The interval 0, 1. So P of an event is the number between 0 and 1. Okay? P of an event is a number between 0 and 1. So this is just the mathematics, like pure mathematics, well, not that much into detail. It's like pure mathematical way of defining probability. But I sometimes find it easier to understand when we talk about when we talk about it this way. So it is a function that assigns to each event that we have defined. So we have taken some subset of S to be our events, and this function assigns to each event a number, a real number between 0 and 1. So that's the mathematical point of view. So let's write down these. Well, there are some interesting things that should happen. It's not just that it takes any event to 0, 1 is enough. No. So let's just put this in some in an axiomatic format. So the axioms are A. Should I say 1 or 2A? Yeah, that's okay. So axiom number A is so axiom for this. So given S sample space and E an event. So P of any event E is a number between 0 and 1. Well, I guess the book uses well, that's okay. So P of event E is bigger than 0. B is put it this way, that P of the whole sample space is 1. And C is P of what the book calls a disjoint union. Well, I will tell you what disjoint union is. So I from 1 to, does it say in, well, so infinity of EIs is sigma P of EIs, I from 1 to infinity, and EIs, E1, E2, a collection of disjoint events. But I didn't define disjoint. I will tell you what disjoint is, but if I were to guess what it means, disjoint event. So let me explain this and also tell you the way that I define that to be a number between 0 and 1 really comes out of these three. So let me tell you what disjoint is. So disjoint is simply a collection of subsets of S that do not intersect. So we say that A1, did I write A or E? A2, A3 are disjoint subsets of S if I intersect AJ is empty for any 2I and J. Okay? So no two of them intersect. No two of them intersect, which means no three of them intersect, right? And so on. So, okay, so if now an example of this thing is like if you have, we will see examples of this thing. So if it is like S, we might see something like this, that this S is collection of some disjoint events. So these are disjoint, they do not intersect. So this means that the probability of these, say these two for example, any number of times, say A2 union A3 is in fact P of A2 plus P of A3. That's the meaning of that sigma. So it means if I have a collection of disjoint subsets, then the probability of a union of them, A2 union A3 union A4 for example, will be P of A2 plus P of A3 plus P of A4. So that's the meaning of axiom number 3. Axiom number 1 was in fact in the definition that probability of an event is a non-negative number. Non-negative means it can be 0, but it's not negative. The second one says that the probability of S itself, the sample space, as a subset of itself. So we always say that S is an event. So we assume that S is an event. Is in fact, say, 1. And the third one, in fact, is telling you this, that if I have a disjoint union of some union of some disjoint events, then the probability of the union, that union is in fact the sum of the probability of those events. Okay, now, one thing which is important is the P of this thing. So remember I said that empty set is a subset of any set. So empty set is a subset of S. And what is the probability of empty set? 0. We can say empty set is like nothing happening. So the probability of nothing happening is 0 if something is going to happen. So the probability of nothing happening is 0. So and the other one is P of S, which we assume that it is in fact 1, and that's like anything can happen, right? So that's 1. So definitely something happens. So okay. So let me erase these things and. See if I can find some nice examples. An example, say, well, remember the gas station, the 2 gas station? Remember it was gas station A, 4 pumps, and gas station B, 4 pumps, and we gathered S was number of pumps at some moment in time, A, B. So this is number of pumps that are active in A, number of pumps active in B, and A and B are numbers between 0 and 4. And we define event E to be, well, let's define some simple event. Event E is A and B such that A is 0, which means if I observe the gas station at certain point in time, what is the probability that gas station A is empty? Okay, so in words, this means the probability that gas station A is empty. This is station A is empty. So that's an event, right? That the gas station A is empty. So let's just do some counting here. In fact, most probabilities are found this way when we have this, what we call discrete probability. So P of this E is what? P of this E is a number of elements in E divided by number of elements in S. And this absolute value, absolute E, is number of elements in E, or outcomes. Remember, we call them outcomes. So some students prefer outcome than element, but that's okay. Number of elements and number of outcomes in E divided by number of outcomes in S. So, let's see. Well, we have it here. So, first of all, S. S goes from 0 to 4, and there's 1, 2, 3, 4, 5, right? So it is 5 times 5, that's 25. This one, the first one is 0. So I have 0, 1, 0, 2, 0, 3, up to 0, 5. This is 5. So 1/5. So with the probability of 20%, that's 1%, right? The first one at certain time, when just assume that you're taking a picture of both of them at a certain point in time, like at 6 a.m. for example, and the probability that the first one or A is empty is 1/5. Which one do you think is well, like you can just say what's the probability that there's one here, just one here, and that's also something like this. So you can just talk about different events and find the probability of that event happening. Let's do another one using that roll 2 dice. So example 2, roll 2 dice, observe the 2 numbers, and A and B. Now what is the probability of, find the probability of rolling a sum of, say, 6. Rolling a sum of 6. So, S is A and B. A and B, both of them start at 1 and at 6. E is A and B, such that A plus B is 6. Okay, so let's find number of elements in S. That is from 1 to 6, that is 6 times 6, 36. This one is A plus B is 6, so well, let's count. So this can be 1, 5, 2, 3, 3, 2, 5, 1. Oh, I forgot one thing. And also, no, not 2, 3, 2, 4, 2, 4, that's 5, right? Am I going 5? 2, 4, sorry, 3, 3, and then I have 4, 2, and then I have 5, 1. So, number of elements in E is simply 1, 2, 3, 4, 5. So, probability of this probability is in fact, let's write it here, that is 5 over 36. So how did I come up with this number? So I said the first one is 1, the second is 5, then the first one is 2, 4, 3, 3, 4, 2, and 5, 1. There's nothing else. Now, usually when we talk about rolling 2 dice, we mean that these 2 dice are different. We can say 2 dice of different colors. Sometimes I say that when I give you a problem, I say that 2 dice of different colors, and this means because some students might say, well, what's the difference between 1, 5 and 5, 1? Yeah, that's true. If you cannot distinguish between them, then they're like the same. But when I say they have different colors, then this is like red, this is yellow. So this is red, yellow, this is red, yellow. Okay, so that is like implicit in problems on rolling dice, that they are in fact, they have different colors. Okay, so these are the 2 simple examples of probability, and let's see. Yeah, I see that the book uses prime, so probability of a complement. So if I have S as sample space and E as an event, what is probability of the complement of E? Okay, let's see. What do we have here? E and EC are disjoint. E and EC are disjoint. Two a subset and its complement are disjoint. You can see these are EC are things that are not in E. This is important to know that E and EC are disjoint, right? Disjoint means what? I guess I did not really. It means that this is empty, right? Oh, I did that. So there's another thing. What is the union of these two? Is the sample space itself, right? This put together with this, so let me write this E inside. So this is not E, this is E, this say oval shaped, and this is EC outside. So if I put these two together, I will get S. Now what is the probability of EC? So let's use this and also use axiom 3. So what is P of E union EC by axiom C? See, this is P of E plus P of EC. And also this is S. So this is in fact P of S, and this is 1 by axiom 1 or 2 in fact. Axiom B. Okay. So what do I get from here? I get P of EC is 1 minus P of E. Now, this is a simple formula, but the way that it's applied, especially when it comes to word problems, is not that easy. Even I sometimes make mistakes when it comes to this. And so, let's see. Let me erase this and so I cannot think of an example, so let's see if there is a nice example. Well, I will come up with examples. I was just thinking of saying that, yeah. So, yeah, this is a good example. So this came to an example. Let's just roll 2 dice again. And find the probability of getting at least a sum of 4. Okay, so at least a sum of 4. So if this is the event E, if this is E, what is E complement? It's important. At least, the complement of at least is just go backward. So at least the sum of 4 means either what? We have 1 plus 1 is 2, 1 plus 2 is 3, right? So these are EC, right? Sum of 2 or 3. So EC is sum, let's write it more carefully. EC is a sum of, I will write this in more formal. So A and B, A comma B, such that A plus B is 2 or 3. And E is AB such that A plus B is bigger than or equal to 4. Okay, so it's easier to deal with this one, right? The sum of 2 or 3 is how many terms or how many outcomes does this one have? EC. It's either 1 plus 1 or 1 plus 2 or 2 plus 1. So this is just 3, right? So P of, say, E is 1 minus P of EC. Well, I wrote this way, so these two are the same. If I P of E, remember P of E plus P of EC is 1. I can write P of E equals 1 minus P of EC, right? That's the same thing. And not the same thing, but they're similar. So that's 1 minus, what is that? 3 over 36. So that is 36 minus 3, that is 33 over 36, which is 11 over 12. Okay. That's a high probability, right? So getting a sum of 4, at least 4, is 11 over 12. Okay, so that is an example of how this rule of complement is used, and so don't forget when we say at least, you can go backwards. Now, most often, nothing always, most often dealing with the complement is much easier. And you will see there are some examples that when we say at least 1, then it goes from 1 to, say, a big number. So the complement means less than 1, which is might be 0, for example. So you will see that the complement is let's say most often it's much easier to find the probability of the complement, and the 1 minus the probability of that complement is in fact what we want. So complements help a lot, and we will see that in future and also in problems that you will be dealing. Okay, so that was the first lecture. I introduced sample spaces, events, and probability of an event, and I explained that that sample space can come up with a real-life experiment. Well, it can come up with, say, I don't know, like if you are testing COVID-19 coronavirus for coronavirus, then you can talk about the number of positives, for example. And just assume that you're counting or number of, say, positives in some clinic or someplace, and so that's like sample space. So sample space will be number of tests received by that lab, and you can talk about an event. Event will be a number of positive cases or number of negative cases. So you can see the complement of positive will be negative. So that is like a real-life experiment, and we will talk about those things in future. That in fact will be examples that I will give you. That's what we are dealing with these days. Okay, so I stop here and see you next time.